So the research presented here is based on work over several years conducted at MIT together with Professor Peter Hagelstein and Sadie Forbes, my colleagues. And Peter presented this morning and Sadie will present right after me, so hopefully the three talks collectively will give you a good sense of what we're doing. And I would like to add that I now also work with Matt Trevithick at Google and with Professor Yet-Ming Chiang at the MIT Material Science and Engineering Department, which is the 6th department at MIT that I'm now affiliated with. So with that, let's dig right into the research questions that are at the center of this presentation. So can energy be transferred non-radiatively from an excited atomic nucleus to another atomic nucleus? And you can see this illustrated here on the right. We have nuclei embedded in a lattice and one is excited, and can the excitation move to another nearby nucleus? And then there's a secondary question: if this transfer happens in an off-resonant way, does that allow for energy exchange with the lattice? So when we talk about nuclear excitation transfer, I should first introduce the notion of excitation transfer more generally. And excitation transfer on the atomic or molecular level has been studied for many decades, even though only in the last couple of years it's been better understood theoretically. And main areas of research that concern themselves with this topic are in biophysics. It's very important for understanding the mechanisms behind photosynthesis. And so in this domain, you would have a molecule that's excited, then transfers the energy to another molecule, and this molecule de-excites. And so people in this research area have very rich literature, and at this point sort of map out the dynamics of pretty complex networks of molecules and how energy transfers within such networks. Here's just a slide to sort of provide more background on this concept of a non-radiative transfer, which is based on a coupling and not based on energy being carried over to an energy carrier, which then has to absorb the entire quantum of energy and then emit it at the acceptor. Instead, you can have a coupling that can be weak compared to the excitation. And here are some examples from the mechanical domain and also the electromagnetic domain. This is basically the principle that's underlying your wireless phone charger. And in both of these cases, you can have a weak coupling and the transfer just takes longer. Although in response to the question that was posed to Peter, there's some dynamics such as Dickey superradiance and so forth that have to be considered when calculating the coupling strength. So returning to experiments, what do some of these experiments look like in biophysics? So you have a molecule that gets excited by a laser and is now in excited state, and then depending on sort of the nearby environment, whether there's acceptors available, either you have a transfer to an acceptor molecule which then emits the excitation, and if you have some loss, that would be at a different frequency. Or if you don't have a suitable acceptor around, the same molecule will emit the excitation. And so here you have some examples from experiments in biophysics where you have the different frequencies emitted from different molecules that either undergo transfer or not undergo transfer. Here's the corresponding energy diagram. And keep that in mind, we'll see very similar diagrams on the nuclear level, even though this is on the molecular level. So where does the excitation come from in our experiments then? We can't use lasers to excite nuclei, but we can rely on the beta decay of radioactive isotopes, which then populate an excited state. So if we have a sort of simple cartoon here where we have a radioactive isotope, cobalt-57, that's part of a lattice, and it beta decays, we have this iron-57 excited state, which is shown here in the energy diagram, and then consequently it goes down through one of two channels, either directly to ground state or through this intermediate step. And then we are mostly interested in this transition here, which is the transition from 14 kV to ground state. So now consider again this cobalt-57 nucleus on a steel plate. And now we consider other iron-57 nuclei, which match the energy levels of the resulting iron-57 in excited state here. And now we add phonons to this system. And phonons then represent this coupling. So if you remember the earlier examples of these coupled harmonic oscillators, that's basically the system that we have here. We have two harmonic oscillators that are connected through a coupling. And the corresponding energy diagram for excitation transfer, nuclear excitation transfer would look like this. So you have this excited state populated, you have the transfer of excitation, you have the second nucleus get excited, this one de-excited, and then you get eventually at the end of the lifetime of the nuclear state, you get a radiative decay. And so the way this would manifest in an experiment is that you have emission from this location, even though you would expect emission from that location. Now you say, can you observe this? This must all happen on very short ranges. And that is true, but if you have multiple transfers, if you have a very large number of transfers, then you can actually reach macroscopic scales and you can observe this in experiment. So some of our earlier experiments looked like this, where we generated phonons in a fairly uncontrolled way with mechanical stress through clamps. We have this cobalt-57 source here, and we have an X-ray spectrometer. And what you would expect from this kind of setup is what you see here. You have the 14 kV line that we saw in the energy diagram, and you would get this slow exponential decay, which is correlated with the 271-day half-life of cobalt-57. And we also see that here on the X-ray fluorescence line of tin K alpha, which is driven by the 122 kV and 136 kV nuclear lines, which follow the same sort of nuclear decay pattern. But what we observed when we applied mechanical stress, about 1 ton force to these clamps, is that we no longer had this expected exponential decay, but we had what we later interpreted as an enhancement during that time at this location. And that would then sort of return to the expected trajectory. And so this is the interpretation that we arrived at, that we have some transfer, so we have some localization of this detection through an aluminum mesh that we use, and we have excitation transfer that then leads to an increase of emission at the site of this detector. So why would you then say, why would we have these dynamics if we have a step input here? Why would we have these dynamics? Well, we also did some secondary tests where we measured the impact of tightening clamps like this in such a configuration. And after a step input change to the clamps, we still have several days until the system returns to equilibrium. So that's kind of corresponding to the timescales that we saw earlier. Okay, but we need better experiments. There's still many unknowns in these experiments. So what we did next is we moved to in situ experiments where we create the stress in situ while we took measurements with a heating pad, which then creates thermal expansion and stress in situ. And from these experiments, we can see a superposition of two dynamics. First one is sort of this long-range dynamic, which is from after applying the clamps initially. And then we see these secondary dynamics that are correlated with the temperature of the plate, and you see the different lines here affected. The 14 kV nuclear line is affected, the K alpha line, which is also driven by internal conversion of the nucleus. And then we have this tin K alpha line, which is unaffected, which is driven by the higher energy nuclear lines. So, naturally you would think we need some spatial diagnostics if we're looking at a spatial effect. So the next step was to take an X-ray camera, look at a sample, which is here shown from the side, apply some mechanical stress. There's a pinhole here to create as an X-ray optic, and then there's an aluminum shield to distinguish between the higher and lower energy lines. So here's an example of a X-ray image of another sample. And here's sort of a zoom in, sort of high resolution focus on this particular area. And also here we observed sort of similar dynamics that differ across different parts of the sample. So we have still lots of data to analyze from this setup and this equipment, but we also noticed that the X-ray camera as such is not the ideal instrument because we don't have enough energy resolution. We can't clearly distinguish between the lower energy 14 kV lines and the higher energy 122, 136 keV lines. And the camera is most sensitive to the harder gammas, not surprisingly. So we focused more recently on this kind of setup where we have an X-ray spectrometer which gives us very high energy resolution and a sample that's clamped onto a XZ stage where we can then raster scan and take images both with spatial resolution and also with energy resolution. So we can get, and temporal resolution of course, but we can get different images for different energy bands of the spectrum. And so here you see the 14 keV image of this sample. And I should mention, Peter mentioned this briefly, that these samples, they're not equal in density. So there's basically three regions. There's the ring, which has the highest density of residue. There's the inside area, which is about 2/3 lower. And then there's the outside the ring, which has almost no nuclei of the radioactive isotopes. And then also Peter mentioned that we know from the supplier that the isotopes are pretty old, so most of the residue that you see here is actually iron-57, not cobalt-57, which is resulting from previously decayed cobalt-57. So with that, here we see an experiment where we see the setup in action. So here we move back and forth every half an hour between those two spots. First we took a full scan to see where we are. Then we move back and forth between those two spots. And we know, and then this is about a 2-week period. And in the middle of this 2-week period for about 2 days, I applied a 50 degree temperature increase, which then created, through thermal expansion, mechanical stress by pressing against the clamp. And we see that in this region, we see about a 2% increase. Which is above the 95% significance bands, and here where we have about a 2/3 weaker signal, but we still, if we had a 2% effect here, we would see it. It would be at this line. So we see clearly a difference between those two pixels in their response to this stress-inducing thermal pulse. And so the interpretation of this result is that what's interesting here is this region of low density and high density. And what this means is, this is of course a cartoon. I mean, there's a lot more, iron-57 in ground state that we would expect. But it's just to illustrate that here you have a higher density, here you have a lower density. So if this is within the range of the transfer, if you have an excited set here, it's more likely to end up on this side than on this side. And if you had an excited set here, it's also more likely to end up on this side. So you would have a net transfer into this high density region. And from the perspective of a pixel, this would mean that you have an increase in that region. But so then you would ask what you would also expect the decrease in an adjacent region. And so that's the next question we investigated. And so we took a full scan. Instead of just 2 pixels, we did the full scan. And this is a difference image. So the image before the stress and during the stress. And we can see here, we see again this increase in the region of the ring, and we also see a decrease in the adjacent regions. And so here I took out the exponential, so you just see the deviation from the exponential, so which is zero, about 0 as we expect here. And then as we apply the mechanical stress, we see a decrease in this region and an increase in this region. And this is about a millimeter distance. So we have a first estimate of a transfer range for nuclear excitation transfer. We did some additional tests. So we took images that can be motion tracked for controlling for any sort of mechanical motion that would account for errors in the measurements. I mentioned earlier the shortcomings of the X-ray, the regular X-ray camera, and those could be addressed by moving to a energy dispersive X-ray camera. So with an energy dispersive X-ray camera, for every pixel, you get a spectrum. So you have high resolution in the spatial domain, higher resolution than with our raster scan, which is slow. You have high resolution on the energy domain, and you have high resolution on the temporal domain. So this would be a well-matched instrument to further characterize and study these effects. Let's think about some implications of what we already learned from, or the sort of preliminary conclusions from these recent experiments. So if we have a 1 millimeter transfer range, that these difference images suggest. And we expect a step size for an individual transfer of 10 nanometers, then we would expect about 100,000 steps within the lifetime of this state. which then translates into a 1 per picosecond transfer rate. So Peter wanted me to make a correction in the early morning. Jet lag team said 1 femtosecond, but it's 1 picosecond. And it's important that the transfer rate is proportional to the coupling strength. And so I'm going to talk in a second about what can be done to increase the coupling strength and thereby also increasing the magnitude of the effect. But I want to consider one other thing first, which is the picture you saw earlier was not quite complete. It was a bit of a simplification. You can also, it was basically representing fully resonant transfer. You can also have off-resonant transfer, where some of the energy gets exchanged with a lattice. And this is also analog to what people in biophysics do. If you remember, you'll see it later again, the energy diagram for electronic excitation transfer also has these lines. And so in nuclear excitation transfer, for each transfer, you can have, in the simplest form, 2 phonon emission or absorption to the lattice. And so that would be a typical value would be 70 milli-electron volts. But so that's way too low to do anything for us. But then if you have repeated transfers, if your transfers are fast enough, which they are at 1 picosecond, 1 picosecond per transfer, then you can have many transfers, and over time you can, in the extremes, build up quite a significant amount of energy that you can exchange with the lattice. So the 2 important variables here are, what's the lifetime of your state? Do you want to have long, if you want to magnify these effects, you want to have long-living nuclear states, and what's the rate of your transfer, which is proportional to the coupling strength. So if we look at this picture, then we have repeated transfers, and as we have repeated transfers, we're building up these off-resonant states, and we're exchanging energy with the lattice. You say, well, how can the nucleus accommodate these off-resonant states? The nucleus by itself cannot, but if it's a coupled system, you have to look at the energy in the entire system and not just in the nucleus. And as the nucleus then radiatively decays, the coupling breaks down, and then you sort of have to pay the, how do you call it? Pay the piper. So what this means in practice, again, for experiments, is that if you have this buildup of energy exchange with the lattice through these off-resonant transfers, you would expect a broadening of the line, of the emission line that you eventually measure from the 14 keV emission. It can be quite easily shown that this is on the order of a couple of EV, in our case, for 100,000 transfers in these experiments. So, and this is interesting again, this is similar to the electronic excitation transfer experiments in biophysics, where you also, instead of a broadening of the line, you see a shift of the line. And that is because in these experiments you only have emission to the coupled system, you don't have absorption from the coupled system. So you don't go higher. Sorry, this is a wavelength, not the frequency. So you don't go higher in frequency, but you only go lower in frequency. Whereas in our experiments, we can go higher and lower. But in principle, it's very similar in terms of, it'd be very easy to understand for this community if we can demonstrate there's a widening of the emission here from phonon exchange with the lattice. But with our current detectors, and we have good detectors which are industry standard, but with a silicon-based detector like the Amtech SDD detector, the FWHM is only 125 eV, so we don't have the resolution that we would need to detect this kind of widening. And the way to get higher resolution is to use a bent crystal spectrometer, where you kind of break up, you kind of mapping the energy to different angles of a circle. So then you kind of scan along your circle, and you can get very high resolution views of your gamma emission. And we actually did this in our group, my colleague Sion and I, where we took a spectrum. We had a crystal that was matched to the about 6 keV state, the 6.4 keV line of the K alpha, and this is data from our group where we actually show the peak, the K-alpha peak, and with very high resolution. So this would be the right resolution, but not the right line. So we need the crystal for the 14 kV line to get this kind of resolution, but we would have the equipment then to show, so we would predict this kind of widening, and we would have the equipment to test for that. So that's another one of the proposed experiments in the future. And then lastly, I mentioned the coupling strength. So increasing the coupling strength would lead to larger effects. One way to increase the coupling strength would be to provide stronger phonons and better match phonon modes. And so one way to do this, which would be a lot more elegant than the poorly characterized mechanical stress that we're working with right now, is to work with a terahertz laser or with a 2-laser terahertz speed frequency. And that's another experiment that hopefully will be done in the future. So how is all of this connected to cold fusion? I've been asked this a number of times. So here, if we can demonstrate with these experiments, if we can sort of fulfill those predictions, then we will have demonstrated that there is a phononuclear coupling and that there is this nuclear excitation transfer mechanism. So we have a toolbox to work with respect to explanations. And if we apply this toolbox to these reports on cold fusion, then the current picture would look something like this. So we have a lattice which has some deuterium pairs, and I'd like to remind you of Schwinger, who said in 1990, 2 deuterons in a close proximity can be thought of as an excited set of helium-4. We have some helium-4 nuclei just from the air. We have some impurities in a lattice, which could be, for instance, a palladium lattice. Here I'm using iron-57 as impurities because we're now familiar with them from the earlier slides, but these could be many other impurities. And what the interesting variables are, again, the energy levels and also the lifetime of the states. So then we apply phonons to this system, and what you would get, you would have a weak coupling between those well-matched states between the 2 deuteron pairs and the stable helium-4. But you have a weak coupling because of the Coulomb barrier. Nevertheless, you have a coupling, and you can have this, what Peter called the null reaction, where you go back and forth between 2 deuteron pairs and a helium-4, which is basically a well-matched resonance. But you don't get anything out of this. This is very difficult, impossible to measure, and you don't get any energy out of this system, which is part of why it works so well, but it's not so interesting to us. But then if you have this happen a number of times, you can get to a place where instead of transferring the energy to another helium-4 nucleus that then disassociates into 2 deuteron pairs, the energy gets subdivided to different nuclei of these impurities, and you populate those excited sets of those nuclei. And then you have the picture that we painted earlier. Then each of those are racing around many times. This is a much faster transfer process now because you don't have the Coulomb barrier. Again, we have an estimate of a picosecond per transfer. These guys can be racing around and build off this off-resonant energy until you actually hit ground state, and everything gets sucked into the lattice, basically. So here's how there's a connection between the cold fusion experiments and this nuclear excitation transfer. I want to bring this image back in because it's fascinating to see this community that has had a lot of activity, a lot of resources. They're at the stage where they also look at these complex, much more complex networks of different oscillators and the couplings between them. And people have calculated these coupling strength. And this is also helping maybe to better understand what a lot of Peter's work is about. When Peter says he calculates the coupling matrix elements, it's akin to some of those relationships. And so then if you have that kind of understanding, you can start modeling these systems and simulating what happens with these kind of systems. So you can have in the future, hopefully, a very systematic approach to a lot of cold fusion and cold fusion related experiments. So the key takeaway points here are: we continue to build a case for nuclear excitation transfer through both theory experiments and hopefully soon also simulations. Nuclear excitation transfer is a mechanism that's interesting in its own right. It basically can be seen as an extension of the concept of electronic excitation transfer to the nuclear scale. But it also, and that's most important for this community probably, it also natively provides a mechanism to account for a wide range of the anomalies that we like to discuss here. Thank you. It's about it's about 2,000 pounds per square inch.
Yes, I have a kind of fundamental question. Since you see the coupling between phonons and the excitation of the nucleus, does this prove or does this not prove whether the nature of nuclear excitation is electromagnetic?
Whether the nature of nuclear excitation is electromagnetic?
Yes, whether you have some electromagnetic phenomenon as nuclear excitation.
I don't think it addresses that question.
You apply this for the cold diffusion mechanism, then you need a very low excitation at the nucleus around the, let's say, nuclear reaction point. You need a nuclei which has a very low excitation energy. And what kind of nucleus are you thinking about? For example, the DD reaction in palladium case.
So there's a bit of a trade-off because this process happens more easily if you have a high nuclear transition, and then this process happens more easily if you have a low nuclear transition.
So you need a iron 57.
So
you mean that?
Well, but then with iron 57, you're having more trouble with this process. You need a much larger, of course, this is, a cartoon. You need a lot more, and with iron 57, you need even more. So the important variable here is the coupling strength. You want to increase the coupling strength so that you can increase the transfer rate. So even if you have a much higher nuclear transition,
how can I change
then
that?
you can, in the tens of keVs, for instance, then you can also down convert from there. And you can increase your coupling strength by having stronger phonons, and you kind of get those stronger phonons by having the reaction going in the first place. So it's.
Is it easier to enhance the coupling strength then?
Yeah, I think the focus should be on enhancing the coupling strength. But of course, the nuclear species that you use are also important. So these are, I think, open questions that are almost more engineering questions than basic science questions in the future to sort of pick the most optimal impurities that for respective applications. And hopefully, having models and simulations will inform those choices. Like people in this community are already engaged.
So how fast will be the de-excitation? Let's say you have a fusion of DD, and this energy needs to be transferred to another nucleus. How fast is that? How many picoseconds or femtoseconds does it take?
So here the estimate from the first experimental results is you have 1 picosecond per transfer, because we have a lifetime of the 14 keV state of about 100 nanoseconds, and we observe about a 1 millimeter transfer range. So that would mean that you have 100,000. That would mean that you have 100,000 1 picosecond transfers.
Mm-hmm. Well, I would also like to comment the situation where you produce especially high Debye phonons. You are expected to produce also discrete breathers, and which also can be mobile and take part in the energy transfer. So these discrete breathers. Anharmonic vibrations. Okay, right. Yeah, because when you enrich the system with phonons, especially Debye phonons, there's been works showing that in this, even in the model situation, this results in the formation of anharmonic vibrations, and some of them may be mobile, also take part in the energy transfer as such, and so it could be that in experiment there's a combination of different mechanisms.
Yeah, I think that, it's a good point, and there should, there needs to be a lot more. This is the very, early stage work in that sense, but hopefully there will be a community of people engaging in this kind of research, and that could be a part of it.
Cool. Well, thank you very much, and